Good morning to all of you. This is part of hydropluvial ecology lab. We are going to have a next lectures on river engineering, and here in these lectures I'll talk about basic properties of sediment. If you look at these three books, what are there is very technically these are selected for river engineering, looking the present context. Like the first books on P.Y. Julien's river mechanics, which talk about mechanics of basic mechanics in river engineering. The second book, which is Pluvial Hydrodynamics, which talks about the advanced level of river engineering, where turbulence properties, the sediment transport properties in present era, how we can model it, how we can understand it more detailed mathematical way. No doubt another books which we have selected is a stream hydrology, introduction for ecologist. So this is the perspective of ecologist point of view, what should be the river and how we should understand the river mechanics. Not only that, we will go through it a series of journals like Journal of Hydrology, American Society of Civil Engineering, Journal of Hydraulics Engineering. Then we will also talk about Journal of Sediment Research. Just before starting this class, I got to say it. This class what have been designed for the faculty, the engineering students, and river engineers who are in the field to take a decisions for a river management. So looking that aspects, this course has been designed. It's not for a theoretical presentations of river engineering, but it gives a practical perspective of river engineering, especially in the developed country like India, how would we can manage the river in better socio-economic benefits, looking for as well as not the short terms as the long terms. Let's go to for today lectures content. We will talk about the river dynamics, we will talk about the river surveys, and then we will go about the properties of sediment particles like particle size distribution curve, which we may have knowledge in geotechnical engineering. Then we will talk about very simple concept of size and shape of the sediment particles, and we will talk about how these sediment mixtures and size distributions concept and angle of reports. Let us start the very basic. If you look at the sketch of these figures, as you know it from basic undergraduate levels, or the river starts from the uplands, the hilly areas. Those uplands are managed as a Zone 1, because in that upland you will have a erosion process, will be active process. There are many tributaries, they will actively erode from the surface erosions, the bed erosions, or the bank erosions. So you will have a significant erosion process which is going to happen in Zone 1. Bed conditions, the river bed conditions will be degradations. That means more deepening and deepening of channels will happen. It channels will have a more confluencing zones, that many tributaries are joining each others. So you can see there are many confluencing zones will happen it when you look at this upland hilly area. From the hill slopes originate the water and the sediment flow. The slopes, here is a steep slope, and most of the bed materials in the river will be gravel or cobbles. So the basically if you look at the Zone 1, which is upland area, the source of water and sediments, it has the dominant process is the erosion process. The river bed will be the degradation status, and you can see their channels are confluencing each others, and slope will be steep, and bed materials more often we can see the gravel bed materials. The size of the bed material is much larger as compared to next zone. Let us come to Zone 2, which is mostly in the fluvial plain regions, where you have the basically the transport purposes. That means whatever the water sediment process collected in Zone 1, that what is goes through this the stretch of the river. that's the zone 2 reach of the river. It just transport the process of water and sediment and the nutrient. So this is the transport mechanisms. It may have the aggregation degradations, but overall it will be the equilibrium positions. That means doesn't change that much significantly the fluvial geometry of the river at this zone as compared to zone 1 or the zone 3. The channels more or less will be the single channels and the slope will be the mild, and here you can see that there is a compositions of the gravel and the sand. So you go to the zone 2. So upland to the middle reach, then we have the lower reach of the river where whatever the sediment carries by the river, it cannot have the transport capacity to carry beyond that part. So that's the reason it starts depositing the sediment part. So there is a sedimentation process happen. Because of the sedimentation process happens, the channels become aggregation stage, means it is rising, the channel bed will be the rising stage. And you can see this lot of branching of the channels, it happens at this reach when before reaching these oceans or the lake. More or less the channels slope will be flat and the bed materials or bank material compositions would be sand and the silt. So I have given very simple pictures. If you start from upland and travel to the middle land and the lower land, you can see that how the rivers behaves in 3 different zones. Upland areas, you will have a erosion process will be activated. Zone 2, there will be transportation process are happening it. When you go for the zone 3, you can see the sedimentation process. The morphology behaviors will be the different, the slope will be different, and the process are different. We should try to understand the river mechanics by doing a field visit, because that is a more important to do any river studies. First we should visit the river. That's what we are showing it in next slides. If you look at that, what the study we have done it for Brahmani river, Odisha in India. So basically if you look at the snapshots, which you in general see these pictures of rivers, but as a river engineering, I can interpret many things about these river systems. Like if you look at these figures, you can see the river is a braiding patterns. It is a multiple channels. The channel bifractions are there, channel diversions are there. So you can see from these figures, there are channel bifractions are there. You can see this bank materials. You go to the take the photographs and see the bank material. How does it look? What are the compositions it has? Is it a sand? Is it a clay? Or is it a sand and clay compositions? You try to analyze it. Not only that, you try to understand what type of stratifications are there, whether the vegetation's presence are there. If the vegetation presence are there, whether the strength of the soil is increased or decreased. So all these things we try to understand it when you do a field visit, take a photograph and analyze it very preliminary level. And we can go for measuring this velocity distributions, the discharge, the sediment concentrations, like equipment like acoustic Doppler current profilers. We can do very extensive river survey to quantify it, how much of water flow is it, how much of sediment flow is it, and how does it varies from locations to locations. We can have the river survey, we can have the field photographs to try to understand it, how things are changing it. So same way, if you look at this, what we do it, many of the river we have intervention systems. Last 100 years we have intervened the rivers in different spaces. Like for examples, there is a barrage structures, there is intervention. Because of this intervention, how this river mechanics changes, the sedimentation changes, how river flow changes, how the morphologies are changing it. So those understanding we should have. Like because of this human intervention systems, because having the barrage, having the small weir structures, you can see that there is a weir, over that the water is spilling it. So because of that, and we can see that way back it 100 years back, the weir structures, because of it's totally silted up. That means you can see that these photographs that it's totally silted up. So all these informations about the river and the river behavior, we should understand it when you go for a field visit. Take the photographs, analyze that what is happening to this river, what could be happened and what is going to happen it. Those, the understanding in terms of water, the sediment and the nutrient, understanding with the different mathematics models, physical models, the field studies, gives us a very synaptic response of the river systems, which looks like a very, at a distance is a complex, but we can look at how it behaves in a simpler form. So basically this course is designed for you to understand so complex systems of water, sediment, nutrient, society, how complex systems we can understand with our existing knowledge on river engineering. So that's the reason. See, this is sandbar formations. If you look at that, it also says a story, but we should try to understand why does this sandbar formations happen, what's the behavior behind that. All we can study it, all we can interpret it if you have a knowledge on river mechanics. Now go to very basic things, that what do we do it? We bring the soil bed samples. We go to the field, take from the bed level, we bring the soil samples. So we should bring the enough number of the soil samples to the lab and do a particle size distribution curve, which is a very simple thing. Through the sieving analysis, we can find out the particle size distribution curve. Or if you have a particle size are very smaller, we can use the hydrometer. So we can get a particle size distribution curve of bed materials or the bank materials. Basically, it is the gradation curve. It's a plotted, or it's a particle size versus percentage of finer. If you look at this x-axis and y-axis, this is a particle size which is in logarithmic scale in millimeter level. You have a percentage of fineness. Beyond this much of a percentage fineness pass through that. That means if I talk about D50 is equal to 0.23 millimeters, that's what is indicating for me that 50% of the bed material particle will pass through 0.23 mm size of the sieve. If similar way you can interpret for 80%, you can 90%, we can interpret it, and the 10%. So this is a percentage of finer, percentage of finers. That means you can have a sieve size, you can find out how much is passing out, how much is retaining it. That percentage in volumetrics, you can obtain it, the percentage of finer. So most of the time, this particle size distribution curve is S curve. Okay, S curve. The shape of this curve is close to the S curve. So to define it, is it a well graded, well composed in the different size? We quantified it into two basic terms, in terms of coefficient of uniformity, coefficient of curvatures. That is D60 by D10 is equal to the coefficient of uniformity. That means you can, from the particle size distribution curve, you can find the 60% finer value, 10% finer value. That ratio will show us coefficient of uniformity. So the particle size distributions, as you can understand it, river doesn't have a uniform distributions. You will not have a single distribution, same size of the sand, same size of gravels. Always there will be mixtures. That's the reason we should try to understand the river mechanisms first, to take the bed samples and see this particle size distributions curve. How does it happen in terms of coefficient of uniformity, coefficient of curvatures, which is in a function of D30, D60, D10, which is a similar things we might have the knowledge from geotechnical engineering. Now if you look at that, we define based on the particle size distribution curve the type of the soils. If it's well graded soil, uniformly graded soils, well graded sand, and the gap graded soils, all are the different soil characteristics. If you look at the A, B, C, D curve, the particle size and the percentage is finer, percentage of finers. So you can see these S curves, okay, for different type of the soils, and based on that we define the type of the soils for us. We use mechanical siever, which is a very simple equipment to take the particle size and have a different sieving sizes, and you just do mechanically sieving the analysis, dry the sieve analysis also do it for the sand and the gravels. Whereas hydrometer methods, we follow it for wet analysis for the plain silt, where we have a less than, the size is less than 75 microns. So you can see the photographs of hydrometer. Let us come to the next one, is about size of a sediment particles. When you talk about sediment particles, that means sediment particles are transport process, the erosion process, and the depositions process, aggradations, transport, and the degradation. These process all depends upon definitions of diameter of sediment particles. We don't define in terms of only physical diameter of the sediment particles. You can understand it if you take a sediment particles, any river, bed materials, you cannot have a uniform size. Also their shape, size also matters it, how it will be transported, how it will be deposited, how it will be start the eroding it. So that's the reasons we define in different diameters, like the area diameters, nominal diameters, sieve diameters, fall diameters, and sedimentations diameters. So we can see, understand it, you cannot have a sediment with a uniform size, okay, that is a natural process. So we will have the mixtures of the sediment particle sizes. So looking that, we define the sediment into the 5 different diameters: nominal diameters, the area diameters, sieve diameters, fall diameters, and sedimentation diameters. And most of the times we don't define the sediment in terms only the millimeter or micrometers, also a logarithmic unit of the 5, which is given it here. We can define it in terms of 5 to scale off, because you can have a very, very finer particles, the coarser particles, or medium particles. So to define the range, we adopt a logarithmic units of the phi to define the sediment particles, which is international standards to define the sediment particles. Now let me talk about these 5 different diameters we use to define a sediment particle size. One is nominal diameters, which is very simple things. You take a sediment particles, you consider as equivalent as a sphere, what could be the diameters, that's what will be the nominal diameters. That means you take a sediment particles which will be so finer, or it can have a gravels, you can look at that once, you make it as equivalent, it is a sphere. If it's as equivalent sphere, what could be the diameters, that's what is the nominal diameters. But if you look it, because many of the process you talk about the surface area, not the volume. So when you talk about the surface area, then we call as equivalent surface area. Here we have considered the volume, but here we consider in terms of surface area. We don't bother about the volume of that part. So if that is the case, what could be the equivalent, the diameters of your sediment particles, if I consider as equivalent sphere of the same surface area? That is the area diameters. Now let's come it, how do we quantify these diameters? It is not easy to measure a simple sediment particles and go to microscope and measure the things. We cannot do that things for a thing. What we generally do it, we do the sieve analysis. That means let us quantify in terms of sieve diameters. But in a sieves, what do we have? We have an opening which is the square opening. We have the square opening. So we try to look it that if a given sediment particle can pass through that, then we call it, that is a sieve diameters. So we try to find out the sieve diameter of that, which is the equivalent of 90% of the dn value. So instead of going to measure the individual diameters at the volumes level or the surface area level. We just do the sieve analysis. From the sieve analysis, we try to relate it as a theoretically we know it will be the 0.9 of the dn value. That's what we compute the dn value. Now if look at other two parties, fall diameters, sedimentation diameters. Many of the sediment transport process, that sediments is try to fall down it. So we try to know it, what could be the fall velocities. So we try to find out in a two-way, again as equivalent to a sphere, find out of having a relative density of the sand, which is 2.65 with a temperatures of the 4 degree, that diameters we call is fall diameters. So this is related to the sediment falls, the sediment depositions process. What it happens it, when you consider that, we will talk about the fall diameters. The sedimentations diameters, if you look at the nest levels, where you try to find out diameter of a spheres having equal terminal fall velocity, relative density will be the same. In earlier case in fall diameters, the relative density we have considered 2.65, but in this case sedimentation diameter, the relative density will be the same as the material relative density. That's the reasons we call sedimentations diameters. So if you look at that, any size of the sediment particles, okay, or the group of the sediment particles, we define them in different diameters, and each one has a own utility in terms of sediment transportation process, the deposition process. Like the sediment deposition process, we are more concerned about the fall diameters, sedimentations diameters, where we talk about the buoyancy forces, the things we can talk about the nominal diameters, we can talk about the volumes, and where is the aerial diameters, we talk about if there is any process happening, the nutrient contents and all in a sediment fluxes. That's what we talk about at the surface area levels. So these 5 diameters is look at very theoretically, but please try to understand it. These 5 diameters we use it to define the sediment properties for different process, depositions, the lifting process, the nutrient carries, and the middle one, the sieve diameter, which is easy to measure the sieve, the diameter of the sediment particles, just doing a sieving and can establish a links between the other part. So please have this looks of these 5 diameters, the nominal area, sieve, fall diameters, and the sedimentations diameter. Now if you look at how do we have shape of the sediment particles, which is necessary for, if you talk about nutrient transport or you talk about the sediment remain in the floating conditions. Again we define as a sphericity, as equal to the sphere, what could be the shape. That's what we define with this empirical relationship, that if it's equivalent to a sphere, that means area of the surface area of the sphere the same volume as given the sediment particles to actual surface area of the particles, that what is defined as a sphericity, and is a simple equations and you can define it. Because volume is a 3-dimensional component, we do this 1/3 to compute it the unidimensional component. But if you don't have the sediment particles as close to the spherical shape, you can have a 3-dimensional lengths in a longest, intermediate and shortest line. So we can have a longest part, we can have an intermediate part and shortest path. So 3 perpendicular axes we can measure that once and you can compute the V values. Same way you can have a BC is the volume of circling the spheres, okay, that is the equivalent part. And there are other people also define the sphericities and in the functions of A2, A3, A1. A1 is a longest length, the A2 is intermediate length and A3 is the shortest length. So it needs to have a microscope, or if you have a gravel, you can measure with a scales. Okay, you can measure it, but if you have the sand, you cannot measure it. But if you have a gravel, you can bring it in, you can measure this A1, A2, A3, and you can compute it what could be the sphericities, which the formulas are given here, and basically as equivalent properties. Okay, same way there are other researchers also given is like Binoni in 1977 define a new factor is called Core-Shape factors, which is in functions of same thing A1, A2 and A3. So definitely this may it's valid for irregular shaped particles. Okay. Similar way we can have a 1960s he has proposed the shape factors is given by again the modifications for that, which consider the distributions of the surface area and volume of the particles. These are looks like empirical equations, but this is what conducting a series of experiments taking the sediment particles, they establish it as equivalent factor for the Core-Shape factors or the shape factors proposed by the Algiers Simons in 1968. Okay, so the basically let's come back to the very basic concepts we use it, that when you take a sediment from the rivers, as I said it earlier, we will not have a uniform distributions. There will be different group of different size of sediment particles will be there. What we do it? We do the sieving analysis. At different size of the sieves, we do the sieving analysis, we find the percentage of finer. But if you put it the percent of size involved and the particle size and draw this curve, more or less it's follow the frequency distribution curve, normalize frequency distribution curve. That's what we get it. That's what is the nature when you take the sediment particles from the any rivers. It follow this, mostly it follow this normal distribution curve. Percentage of size in the sediment size. But if you make it a percentage finer, you will have a cumulative distribution curve, which is so often you use in any statistical analysis the normal distribution curve as probability distribution function, cumulative distribution curve is probability density function. So you look at these distributions which is follow many the populations, any populations, you can see that it follow a certain distribution, the normal distribution curve, and the cumulative of that, this is what the cumulative frequency curve. Recently people try to fit a normal distribution curve and try to find out whether we can define it, the sediment particles in terms of distribution functions. So not just a 50% finer value or D50 or D80 or D90. Instead of that, try to understand the sediment properties more details. They follow a probability distributions concept. Like if you look at that, it has given us the distributions file, which is log normal distributions file, and if you do a cumulative functions, which will have a error functions on this. So we can have a distributions file like this. So you can find out, if you know this D50 value, you know this sigma z value, you can compute for a particular D what will be the probability distribution function and what could be the cumulative distribution functions. I just encourage all of you, just use a MATLAB or any Mathematica softwares to just draw different D50 value and sigma g value to draw the normal distribution curve followed by the cumulative distribution curve. So if you look at sigma g here is defined as geometric standard deviations. Again I am happy to take it. It's not a standard deviations. It's a geometric standard deviations of particle size distribution. That's you try to understand it, the soil compositions, what we will get it after receiving it. It follows the normal distribution curve, but it doesn't follow the standard deviations. It's follow geometric standard deviations. How to quantify that? The D50 is the 50% median value diameters or 50% particle size, which we can obtain from curve. Now let us talk about how to compute the sigma g. which is geometric standard deviation. How do you compute it? Which will be functions of non-uniformity of sedimentary mixtures. That's what we are targeting. Which will be a function of sigma j will be a ratio between D85 by D50. So the particle size for the 84% finers, the particle size for the 50% finer, which we can get it from particle size distribution curve, or you can have a as equal to D50, D15 point and all. You can compute it the finer diameters. You can find out what will be the geometric standard deviations, or there is a geometric standard deviations in terms of D85. So that means again I have to draw it. So you have a particle size distributions for the 15.6% finers, you can get it D15.9. similar way for you have 84.1, so you can get it D84.1, and the square root of the product and the square root of that will give it the geometric mean of that. If the geometric standard deviation is lesser than 1.4, then we call the sediment can consider as a uniform, otherwise non-uniform sediment deposits. Many of the times we do the flume experiments to tell it is it a uniform sedimentary distributions or non-uniform distribution. That's what we quantify in terms of geometric standard deviations, which we compute from particle size distributions curve. More coefficient called gradations coefficients, which is again capital G, which is a functions of D50, D85 and D15.9. Okay, these are. Now if you look at these other parts, what we are talking about, the angle of repose. If you look at that, in a river there will be sediment depositions. We try to look at what could be the angle of equilibrium angles that sediment depositions can have in it. You can do a very simple experiment, take a sand and just pour the sand. If you see that it remains at a particular angle, beyond that it starts falling it. So this is the concept we will talk about, how that angles happen, the steepest angle of the descent of a slope with respect to horizontal plane. Okay, if you look at these ones, when the sediment particles submerged in the waters on the parts of the sliding on the slope surface on a sediment heap. You can conduct this similar experiments. Okay, very simple experiment. You have a container, fill up the just fill up the sands and you see that at what point that slope will maintain it. You create the heap and you try to look at what is the angle it can maintain it. Or if you look at the microscopically, okay, the sand particles, if you look at the microscopically, there will be a hydrodynamic drag will be there will be submerged weight, there is a balancing between that angles we define as angle of repose. This is equivalent to pivoting angles of phi, which is superimpose the particles resting on the bed particles at the point of the contact over P. It can see these figures. This angle is known as angle of repose. Okay, this is what is necessary for us to know it, whether the sediments, the heap is stable or not stable. And these values for the sediment is values varies from 28 to 30 degrees, and most of the times we consider is 30 degrees enough for angle of repose. Many of the times we go for more details, like for a non-cohesive soils like a sand soil, we try to find out what could be the angle of repose with these empirical equations which establish relationship between angle of repose and the D50. D50 stands for diameter at the 50% finers. So we can empirically establish it, what could be the angle of repose if we know the D50 value. So we can find out the angle of repose. But this equation is valid for this range of the D50, which is vary from 0.2 to 4.4 millimeters. This is the range, this equation is valid. Whenever you apply the empirical equations, look at this validity range, because this equation is established for this the range which is valid these equations. So please don't use these equations the D50 beyond 4.4 mm, because this equation is not valid for that. So try to understand it. The empirical equations are developed for a certain range of the data, and that's what we should look at before applying this equation. Same way we can have a more details to determining this angle of reports. So please go through the books of fluvial hydrodynamics or these materials to have a look about these empirical equations. And before ending this class, let me bring it very simple idea. If you look at this sediment carrying the river systems, that means water is there and the sediment particles are there. That means volume of the fluid and volume of the solid. In the river we have two compositions, one is water, another is volume of the sediment. So water, fluid and sediment mixtures we have. So if that is there, if I to quantify what is the sediment concentration in terms of volume, that means how much of concentrations I have, the volume of sediment divided by the total volume will be the V plus VF plus. So that's what the, in terms of volume, how much of area is occupied by the sediment particles. Let's talk about the sediment concentrations C by the volumes. When we talk about the volumes, we can have a volume of sediment by the total volumes, which will be Vf plus Vs. So we can calculate the volume, the sediment concentrations. So it's a very simple way to know it, how much of concentrations are there. Higher the presence of the sediments, higher the sediment concentrations. So C will be the higher value. If low sediment concentrations, that means Vs will be the less, C will be the less. But many of the times we do a mass conservation properties. Okay, we don't look at the volumetric levels. When you do the mass conservation properties, we multiply the density with the volume to get the mass. Like what could be the mass of the sediment particles are there, which will be rho s into Vs. Rho s stands here is the density of the sediment particles into Vs is the volume of the sediment particle. Same way, if I just multiply it, I will get the sediment concentrations by mass. This is by volume. That's the different. So we talk sometime the sediment concentration in terms of volume point of view or in terms of mass point of view. So the C value will be the different, and many of the books we define into the capital C or the small c for sediment particles by mass. Besides that, we talk about a mixture. Fluid and sediment is there, but we don't try to make it the different, we mix it. So we can have a simple linear mixing concept. You have a sigma, you have a sigma s, you have a buoyancy force part. So we can compute it, what could be the mass density, what would be amount of mass will be there. Similar way, we can have the specific weight, the mass density multiplied with the g, which gives us specific weight. The kinematic viscosity, we can, for the fluid and sediment mixtures also we can define like a fluid mechanics, the dynamic viscosity by the rho, and the dynamic viscosity from the experimental results, if you look at it has been established in functions of capital C. Here the mu stands for dynamic viscosity of the clear waters. As the sedimentary concentration changes it, the kinematic viscosity of these fluid and sediment mixtures is changes it, and experimentally it establishes it. It follows the as a functions of mu is the dynamic viscosity of the clear waters with a multiple constant as it's given it, as a multiple constants which is a function in terms of capital C. Or there is an empirical relationship which is a Lee 1969, it has given is in terms of a power functions. So these are all empirical equations to establish, to find out what is the kinematic viscosity of fluid sediment mixtures, because when a river is flowing, it's not only water is flowing, it's flowing water and sediment. So we need to know it, what could be the viscosity, which will be the functions of the mu is as equivalent dynamic viscosity of clear waters and function of C, the sediment concentrations in terms of volumetric sediment concentrations. These are the empirical equations is established for Lee 1969 and Baglon 1954. It established it what could be the edge equivalent is kinematic viscosity of fluid and sediment mixtures. With this, I come to summary of these second lectures. Most of the things we have talked about, mostly we are bringing in the concept is that like a nominal diameters, area diameters, sieve diameters and fall diameters and sedimentations diameters. We talk about the frequency curve, we talk about cumulative frequency curve. We also talk about how we define it, whether the sediment mixtures are uniform or non-uniforms, and we talk about geometric standard deviations, what we use it to find out what could be the sediment and whether you can consider uniform sediment or non-uniform sediments. With this, let me thank it our group. We have been extensively working on river morphology, river hydrodynamics across the India, global scales. We have been doing a lot of river studies. No doubt we will give you to a lot of exposures of what level of the difficulty we face it, how solve these complex problems in different part of the world. So these are my research groups. We have been preparing this material for you, Chandan Pradhan's, Ketan Nandi, Ridik Kakoti and Sahu. And end of these lectures, let's we talk about the quote as given by Binita Karina. If Ganges is the mother's, Himalaya is his father's. One nurtures, nourishes, the others provides and protects. So looking this quote, we should look at the river beyond just a water flow system. With this, let's us conclude this lecture. Thank you.